Performance Expo viewers, welcome back. We got a real surprise for you today. Super excited about this. We're here at Petty's Garage. What an amazing place, all kinds of great history. Again, I'm Lake Speed Jr. from Total Steel Piston Rings, and my buddy.
Hi, I'm Dan Begle, Mahle Performance. I'm an engineer for Mahle. My background, 27 years in NASCAR, built a lot of engines. I was fortunate that when I came aboard Mahle, I got to work with the engineering and manufacturing to see how things are made. There's things I did when I was building engines and you kind of question, why am I doing this? Or did I hurt anything doing it? Now, I realize some of the stuff I did probably wasn't too smart. Some of the stuff I learned why we do, and designing the engine bearings, it's been a lot of pieces of the puzzle been able to put together in my career. So hopefully this you find helpful and beneficial to learn some stuff about bearings. So looking forward to it.
So that's the cool part, right? You know, myself, growing up in racing around NASCAR, used oil my whole life. Then I go to work for Joe Gibbs. We have an oil company, and you learn how oil is really made. Changes your whole perspective on everything. So for you, I said, coming from a NASCAR background, say 27 years.
It was a long time. The last 9 years, I was the reliability specialist at Roush Yates. So
you looked at lots of bearings.
I looked at a ton of bearings. I looked at after the race, if there was a failure, tried to determine what was going on. If there wasn't a failure, just trying to find where wear was happening, different things going on with the crankshaft, and of course the driver errors. Like, you wouldn't know anything about any driver errors.
No one's ever missed a shift. Never. Not.
Yes.
So then going to work for Mahle and actually learning how the bearing's made, transformative moment.
Absolutely. It's wonderful. I've spent several weeks at different facilities that we have with engineering on the plant floor. I've been to our Scotland, where we make bronze bearings, just a magnitude of things, and it's very interesting.
Well, what's cool to me about a bearing, right? So fairly ubiquitous part, right? They're in every engine, all over the place, and they look pretty simple and plain, right? We call it a plain bearing. Actually, terminology for it. But yeah, I think about going back to some of the shops over in England and stuff, where these guys are literally pouring babbitt and boring, the old engines. And now we've got these inserts, and the first thing I think of in my head is, wait, how did they get the right eccentricity to that poured bearing when they were just boring it with a bar?
Well, if you think about it, like Model T came out with lead bearings, bored. So it's bored two sides. So basically, you're just boring that whole round the same as the shaft, a little bigger. There's no eccentricity on there, but they only made 20 horsepower.
Okay. Right, so as an oil guy, right, so to me, the bearing is one of the coolest things in the engine, actually, because there can be no additives in the oil at all. There can be no zinc, nothing, just base oil. If you get the viscosity right for the speed and the load, like you just mentioned, this thing will be super happy.
So when a bearing's made, we're going to get a
big one, right?
We're going to get a big bearing here, so it's a little easier to see. So in a bearing design, you have this dimension here, right here, which would be your 12 and 6 o'clock position, is where you set your oil clearance at.
Right.
Okay.
That's where you measure to get the clearance, because we know out here is going to be a little bit wider.
Right here, you're spreading out. So there is a dimension when we bore this out. We bore it so it's bigger. It's offset bored.
Okay.
So this creates a wedge.
Right.
All right. So it's thinner here and here than it is here. And also, right on the very end, there is what we call bore relief. Okay. So if you have some misalignment or connecting rod that is flexing, you don't want to pinch off the oil wedge. Right. So my best way to explain what happens here is you feed oil coming into the bearing, and it creates a wedge. It's kind of like a door wedge, a door stop underneath the door. So the harder you push the door stop underneath the door, the more it tries to raise that door up. Same thing with the oil. So if your oil comes in, you're creating a large amount of oil, larger volume, and you're trying to squeeze it to a smaller area. Right. Which, of course, at that point, you're creating a higher pressure, which is lifting the crank off there. Right. So now a couple things, and you're talking about oil viscosity, and if this clearance here, how much clearance you put between the crankshaft and the bearing is very relative to how much viscosity you run.
Preach on, brother. I say that all the time. The number one thing in importance is oil viscosity and bearing clearance must go together.
Have to. So you have to know what in your mind what oil you're going to run. When you build this engine. So if you're going to build an engine and you run real big clearances on that engine, you better have some real thick oil. Right? If you're tightening up your clearance, you better have some thinner oil, because you can't take thick oil and squeeze into a very small area.
I love your analogy of the wedge, the doorstop wedge, because when I think about viscosity, one of the analogies I use for that full film is sheets of paper. Right? So if you have a big stack of paper together, that viscosity is actually the resistance between those sheets of paper. So what you're trying to do is actually jam them in there, and it's the rotation of the journal that's actually drawing and dragging, because that viscosity is all it is a fancy word for resistance to flow. So the higher the viscosity, the more resistance there is, the easier it is for that crank to drag it in there.
Absolutely.
But it's going to start to push in. But if you can't get it to flow and go, then you can't get enough there.
Correct. So the other thing, with the oil getting right, because a lot of people don't realize, when going on, your oil flow, your oil movement, in this case, if the crankshaft is rotating, is wedging in here.
Right.
Now, when that engine fires via a rod bearing, this would be a pretty big rod bearing.
Go with it, So there's diesel guys out there who say, that's these tiny.
Yes, exactly. So on a performance engine, you have a lot of cylinder pressure. When the cylinder pressures, the other thing that happens is you lose the film by squeezing it.
Yes.
So at that point, if this being an upper, the engine fires, you are trying to squeeze the oil out here.
Right.
All right. So that's crucial also to know why you have enough clearance to create enough oil wedge that when your engine is firing, that your squeeze film doesn't come through where you start getting crankshaft.
Metal to metal is not a good thing in this case.
It's not happy. Not happy.
It's definitely not a camshaft in a lifter where that's normal life, and we designed it for that. This definitely not.
Absolutely. So part of the thing is designing your build around there. The other thing is there's different oil grooves.
Full groove bearing.
Full groove. Right. So in this case, when we build a bearing, when we design a bearing, we want to know how much flow is going into this bearing. That's calculated because it's based off of hole size. It's based off of cross-section area of the bearing of the slot in here.
Okay.
So, as I mentioned earlier, you have a bore relief right here. So as your bearing would fit together, you're going to have leakage at your bore relief. Right. So to increase the flow, what we can do on certain applications is we have made less than a 180 groove, whereas you can see it is coming down to maybe 130 degrees or something like that. The purpose of that is to get the oil to stop coming all the ways down to the bore relief, which is the widest part of the bearing. Now, it still gives you room for cap misalignment on a main or rod flex or misalignment on a connecting rod.
Rods flex?
Yeah, they do.
In some applications, they flex a lot.
That's another show for another time. So we have a certain amount of flow we wanted to get through there, and to keep the oil wedge in there, sometimes by making it a shorter groove, you can create more wedge by not having an exit path for the oil to come out into the bore relief.
Okay.
So it's one of the things. So we figure out how much oil flow it has. Now, there's been some talk about restricting oil flow holes.
Yes.
That's a great concept. I'm working on some data on that on our data acquisition that we have. We're trying to work on what you can do, because part of pressure coming through the main bearing to the rod obviously has to go through the crankshaft.
Right, exactly.
Okay, so there's several factors happening in. So as that oil hole is in the crankshaft is getting away from there, it's no longer feeding the rod.
Bingo.
So you only have how much oil is in between the main and the rod.
Right.
So there's several things. You have that pressure, you have centrifugal force pressure,
Right.
and then obviously how much oil by the hole size, the length of stroke, the RPMs you're turning.
Right.
There's a huge amount of that. So, you know, caution people with the hole size of I'm going to restrict oil flow. Restricting oil flow is a lot done with how much bore relief it has and the eccentricity of the bearing rather than just decreasing the oil, because the end result is the rod bearing may have a starvation problem.
And that's what we see all the time, right? My experience doing oil analysis and, you know, selling oil and oil engineering for a long time, you typically are going to see the rod bearing fail before you see the main bearing fail.
Absolutely.
And it's because it's the end of the chain, right? It's like, oh, because if you run it out of oil, it dies.
My failure analysis at NASCAR, that's usually the case. It's very seldom a main bearing. It's usually, remember this big rod bearing we had?
Yeah, the main bearings rarely fail. When they do, you're like, we had a really big problem here.
Absolutely.
Which again, it can happen sometimes, right? Now, see,
Sure.
and the rod bearings they're also kind of challenged because if the engine is detonating, back to that squeeze film, now you're really hammering it.
Right.
And in some of those other odd cases where you can get that rod elongating and stretching, you can get that cavitation, because you can start to see some weird things in the bearing. Obviously, your experience reading bearings after races, why don't you talk a little bit about some of the things to look for, common things to kind of read those bearings after being used, so they can kind of tell you, because they're trying to tell you a story.
Right. And I always say parts always have a story. It's knowing what they're saying and be able to understand their story. Reading it is the thing. You know, a lot of things, like said exactly. I mean, rod bearings, I get pictures all the time, people sending rod bearings to me, and the lower has a lot of fatigue. Fatigue is when the overlay is wanting to move, and it's before the overlay would be a failure, but it's moving. And there's only so much movement it can tolerate before it starts cracking.
Right.
And in different overlays, we have overlays of a lead indium that will allow it to move more, and we have a copper tin lead that doesn't allow it to move as much, but it will give you more service life. So you kind of have to know what bearing you want based off how much service life. So in what examination of it, if you look and you have a hard bearing with a lot of cylinder pressure or a lot of crank flex, you get fatiguing, where you get the spider web look on there. The lead indium is allows it to move more, and at that point it comes back to its form and it doesn't fatigue. But it's a softer bearing, so it won't give you the 100,000 miles you want on your street performance car.
Got it. That's why like the sprint car guys and that, man, you can't take that lead indium bearing from them. They got to have it.
Yes, because there's so much deformation going on in those cars and some other applications. If you have a clutch that comes in or a guy's doing a burnout and there's a lot, you can get the starting to whip around.
Oh yeah.
And it's not common. People say that can't happen. Yes, it can. I've seen fatigue on one side and fatigue on the other side that the crank is whipping so bad you can get spider webs on one side and spider webs on the other side, and the center looks perfectly good. That's how much.
That's why we got him on here. Right. So you did a webinar for AERA earlier this year. And
AERA.
Yes.
Oh, yes.
Right. That you actually showed a great analogy or an example for what that looks like.
Yes.
Please explain to everybody, because I don't want to steal your thunder, because it was your idea. It was brilliant. If you've ever seen that fracturing, cracking, spider webbing of a bearing, please explain what your analogy was.
Well, before we get in there, I want to explain a little bit. A bearing's made, and there's a substrate that's put on there. It starts with a steel back.
So steel on the back.
Steel back, and this is a copper lead mixture that is put on the steel back.
Okay.
So that's the two parts. A tri-metal bearing, which let's jump over here. A tri-metal bearing is one that would have the steel. It would have the copper substrate and then an overlay on top of it.
Okay, what's the overlay material?
So the overlay would be a copper tin lead on like a standard performance street application,
Sure. Yep.
heavy horsepower.
Yep.
And on a extreme application, it's a lead indium.
Okay, so would this be considered an H bearing, or
This particular one, it could be either one.
either one? Okay.
Either one. The difference is going to be what the substrate is.
Oh, the difference between H and a P is the substrate.
It's the substrate.
Learn something every day.
Yes. So the H and P, it starts out with steel back. HPRV.
Okay.
They're all the same.
All right.
Okay. Now the difference is they're a tri-metal bearing.
Yep.
But that's about where it stands the difference.
Okay.
P bearing.
All right.
A P bearing is a centered bearing.
Okay.
And what a centered bearing is this copper lead mixture is mixed together.
Yep.
And it's laid on top of the steel backing.
Okay.
Once you're laid on top of the steel backing, it's heated and squeezed, called sintering.
Okay.
That's, at that point, your strip is done.
Got it.
The cast bearing is the same thing. And this is a picture of the cast bearing.
Yeah.
So
And you can see the grain structure
there's
is
a
completely different.
tremendous amount of grain structure. So when you cast the bearing, you take a copper lead mixture, and in this case, you would fold these two ends up, right?
Sure.
And it makes a little trough, and you melt the copper lead to 2,000 degrees. 2,000 degrees is the point right above when the copper melts.
Got it.
Okay, so when it cools, it melts the molten copper lead. Comes in here, it lays on the back. And if you ever look at a bearing and you notice that there's a bluish tint on the back of it,
Yes.
well, that's from the 2,000 degree copper lead.
Makes all the sense in the world.
So you've tarnished the bearing. And just for record, we do hardness check the backing, so we
Make
know
sure that it's not
we calculate in that so the back of the steel backing stays where we want it within spec.
Awesome.
Okay, so this is a P bearing. I've noticed there's an actual finish bearing.
Right. It doesn't have that color.
Doesn't have that
Because it doesn't get that
it's
hot.
centered. Now
Right.
you take copper lead and you melt it, so the copper lead cools at different melts or cools at different temperatures. So the copper will cool and it will start to it gives it better adhesion to the steel.
Makes sense.
Lead does not adhere to steel.
Yeah.
Okay, so a centered bearing, you can have lead right on the center on the steel backing, and you can have a delamination where you lose a whole part of the bearing. That's why people put a P bearing on too much performance, and all of a sudden a part of their bearing is missing, and they go on the hunt of what happened.
The delamination is because the bearing
had a lead part, and the lead will not adhere. It's kind of like soldering, and solder falls on the concrete floor.
Yep.
It won't stick.
Right.
So the copper will stick to lead. So the copper cools first, and then the lead. And when it molts together, because of the cooling of it, it will create grain.
Got it.
Which is structural strength. It's kind of like building a house. All right, you can build a house with 2x2 walls, or you can build them with 2x6 walls.
Right.
The 2x6 walls is a lot sturdier for your roof via the overlay.
More grain, more strength.
20 to 30% stronger.
Okay, there you go. So what you're saying is the H bearing and the P bearing have the same overlay, but the substrate is different.
Correct. So the P bearing is the centered bearing.
Okay.
Which has the issue with P bearings in performance is there as you melt the copper lead.
Yep.
You can have lead that hits the steel, and lead does not adhere to steel. Right. So you can have a delamination of a chunk of the bearing comes out. You're going.
I think people have seen that before.
Yeah. And it's like, what happened? Well, there's a couple things that happen in a centered bearing. One, the adhesion. There's lead does not adhere. Two, you can have larger areas of lead, so you can have a soft spot in your bearing. Okay. Which at that point will cause the overlay to move, which will cause crack propagation down. Right. Third thing is right off the bat, because of the way it's formed, you can have cracks in the substrate because it's not cast. Got it. So you automatically, and externally, they all look the same. But you can have cracks in there, and when you start putting stress on there and firing load, cylinder pressure, crank torsionals,
That's why the cast bearing is stronger because of all that grain structure.
Correct.
Gives it strength.
Yes.
And that strength is what makes it better for a higher performance application. Then you go from that same copper tin lead overlay to the lead indium overlay, and that's a V bearing?
The V bearing, lead indium.
Okay.
So the indium allows the top, the plating, to move.
Okay.
It can move more and retain its same shape.
All right.
So that gives ability, but the downside to the V bearing, if you want to run 100,000 miles, it's a softer bearing.
Okay.
So it conforms, you have to balance.
So it's softer, but it can move, but it doesn't have the fatigue life, essentially.
Correct.
Or is it fatigue the right word there?
It won't give you the service life.
Service life, okay.
Because it's not designed to run 100,000 miles. It's designed to withstand a lot of cylinder pressure or crank torsions that crank whip.
Top fuel bearing.
Top fuel bearing is always a V bearing.
Got it. Yeah.
Anything like that, even down, 3,000-4,000 horsepower, V bearing is the way, because there's so much that happens, and you reach a point you can balance. I can get by with an H. You kind of have to look at what are you expecting and how good a tune and how good a tire.
That's the thing. Yeah.
Because a detonation can knock out squeeze film.
Yeah.
We talked about that earlier.
Right.
So if you detonate, or in some cases, I've had people sending me pictures of engine rod bearings, and they're two identical cars. There's two named drivers. I won't mention them right now, but they had team cars, and they're like, why does one look like this and one doesn't? And we come to find out, driving style, one would be on the rev limiter, both cases. Whether one was a drag car, one was not.
Right.
But one drove on the rev limiter. So when you're knocking that cylinder out, you're rattling and firing, and you're losing your squeeze film. Hence the reason you see on those applications, you can actually see contact of the crankshaft on the lower rod bearing, because you're losing the squeeze film. And engine firing, 4 cycles, right? Yep. The exhaust cycle, there's nothing stopping that piston.
Exactly.
So that piston's trying to go out the exhaust port. Yep. The lower is trying to go send it out. Yep. So it's interesting when you see that. Like I said, all parts have a story. It's knowing what they say.
So if you've got an H bearing and you're seeing that spider web cracking, is that a kind of sign that, hey, you should go to a V bearing?
Not necessarily.
Okay.
Not necessarily.
Right.
So unless you're having some delamination where the bearing you're seeing it starting to chunk out. Okay. Because we can make a bearing that will outlive the crank, but you don't want to be replacing crankshafts all the time.
Good point. They are kind of expensive.
So you have to realize when you're building an engine, what is the tangible parts, just like you don't use gaskets over. Right. Bearings are the part that save your connecting rod and your crankshaft and your block. Fair. Right. You need to allow and
that part can be expendable. The other parts you want to keep them in the surface.
But you don't want it to get to a point where there's so much fatigue that you're starting to lose. You're seeing copper come through. Okay. Or you're possibly getting so much fatigue that it's blowing out the overlay or plating, whatever you want to call it. And at that point, you have to look at it. Some of it, to have some spider webbing in it and fatigue, it's just showing that you've worked the bearing and it's did its job. Not that it's a failed part.
All right. So now you got to tell them the Jello story, please. Okay. So about fatigue and that cracking, because it's a hard thing to explain to people.
It is a very hard thing to say. So I had this wild idea one night, and I took a glass bowl. I had my kids make me some Jello, and
orange
Jello because it matched the substrate. All right, so it all looked good, and from there I took the Jello and it was set up. Yep. And I took some black spray paint and I painted the Jello.
Coated Jello.
So I coated Jello, absolutely. Plated Jello.
Plated Jello. Yeah, exactly.
It looked really good, right? So not that I want to eat it, but it looked really good. No. The problem lies into, all right, so what that represents was the glass bowl with the steel back. Yep. The orange Jello being the substrate. And the paint over top was the overlay. Yeah. Right? So it all looked great until I had some torsionals on the bowl. I shook the bowl. Right. The Jello wiggles, being a centered bearing versus a cast bearing. So the substrate
started to move. Yep.
And the paint cracks all over it, representing fatigue. So
brilliant, perfect, best analogy ever for that. You know,
it was the easiest way to explain it. I do have it on slides, so it was pretty fun. I'm not sure my kids will ever make me Jello again. That's a whole other story.
It's okay.
So it is. The part's going to move, and you're going to see fatiguing in there, and it's just showing that the part's working. Yeah.
It's a great way of saying it. It's not something to be, oh my God, this thing's imminent failure. It's like, no, you're working the part, you're seeing that it's working.
Yeah.
And that's not a bad thing.
That's not a bad thing. Now, what you look at, you know, I was big about looking at all your bearings and all your mains together. And if you can stack all your mains together and all your rods together,
yes,
and you analyze and look, and you can see different wear patterns or something like that, what you're reading, the fatigue lines, the fatigue fractures, are telling you what is happening, what the crank is moving. Is the crank whipping? Is it moving left to right? Again, your rod caps, are you seeing wear on there? Are you seeing polishing marks on the upper that you're losing your oil film? There's several things. It's knowing what those parts are saying, but you know, a lot of people don't analyze their bearings like I wish they would. You're building a lot of power, and you take the bearings out and they go in the trash can because they're throwaway parts, right?
Yeah.
I get it. Yeah. But again, the parts have a story to tell. It's like if you're working on where am I at on my limitations of power, or my crank design, or my counterweight designs, or anything like that, you have to look at what the parts are showing you. Where
and what you're saying to do is take all those main bearings and put them all together side by side in the order they are in the engine.
Absolutely.
And then do your rods the same way.
Absolutely.
And then you look at that whole story, uppers, lowers, mains, rods, and then say, okay, what is it? What do I see?
Right.
Because am I good here, but I'm terrible here? Okay, maybe my crank's doing this.
Right. And oil feeds, because if you feed from the front and your back rear, you're starting to see more polishing on your rear rods than you are the front. Are you having an oil flow issue?
Right.
Are you having an issue where you have fatigue on certain cylinders because maybe they're hotter cylinders, they're making more power than another cylinder is? You know, back to the fuel cars. Fuel cars tune off of how flat the bearing becomes.
How
much you lose. So you go through and you measure, and that tells you, you can figure out your hottest cylinder, and you know that's most time usually your weakest link, because that's the one that's making the most power, and that's the one that's going to give you problems. So
that's the one that's on the edge.
You have to know where your weakest link is.
Right.
And again, bearings are a great tool if you use them properly and take the time and lay them out, look at them, and study what they're saying, because they show you the signs.
Okay, so I have another question for you, because here on the Engine Performance Expo, and we're building an engine, and we're, because of necessity, being this is 2021, and power supply can be a challenge, we're putting an aluminum rod in the engine as a way to solve a problem. We won't get into it in this video, but talk about what that difference is. We know it's the bearing crush, not the tang.
Yes,
that holds the bearing in place, right?
I don't have that argument with people. Yes.
So yes. No. So how do you treat an aluminum block or an aluminum rod different than an iron block or a steel rod?
Great question. Yeah. So when we design a bearing, it's different. This is actually considered the length of the bearing.
Okay.
So when we put in there, and we'll put in a fixture, and this part of the fixture, let's say, is at deck height or zero height. Okay. So there's. And this part, we have a number that we want that will tell how much it's standoff, what we call standoff.
Right.
And there's amount of force that's put on this bearing, with this being kept at zero.
Okay.
A certain amount of force, and then we'll measure this standoff. So what you're doing is, in designing the bearing, we recommend a specific housing bore.
Yes.
All right. So one of the things people do is they change the housing board to change oil clearance.
Yes.
That's a big no-no, because
you hear that?
Because what you're doing is you're taking away the standoff.
Correct.
And the standoff puts stress into the rod or block to hold it, because remember, again, it's not the locating tang, it's the amount of force that's put into the bearing. So you want to have it right so it puts enough force in there, but you don't want to have too much that you would actually be able to cause a buckle.
Right, yeah, exactly.
It can actually buckle the bearing. So
because that would then mess up the wedge, because you've got this eccentricity that's trying to feed the oil.
Absolutely.
If you buckle it, now you've messed that all up. You
have a high point which will contact. So the other, what you see people is like, okay, I don't want the bearing to move, so they can go the other extreme, and now they have the min-max spec of the housing bore, and say, well, I'm going to put smaller. Okay, well, the smaller you risk buckling the bearing. The bigger you can risk not enough.
Not having enough crush, and it spins the bearing.
And it spins the bearing. So on all those cases, you know, if you're using aluminum, there's some applications that we have made bearings for that specifically for aluminum, high-end race applications. Like we make a big block Chevy aluminum block bearing. Got it. For racing applications, specific for that. It's a V bearing.
Yeah, it makes sense.
V bearing.
Because you know that housing bore is going to grow more, so you basically compensate for that
by putting more standoff in there. Okay, so because the big block Chevy was a cast iron block, so if block is designed with a big block Chevy main with a cast iron, and you get enough crank torsionals go through it, you can have the bearing either want to spin, or in some cases they'll actually walk back and forth. And that's, you can always tell that because it will start rubbing on the side of the bearing, and usually it will do it on the non-tang side because the tang is located.
It doesn't want to move,
and the bearing will actually flex front to rear.
How about that?
You can get the radius, and you'll see it on this side, and it will diminish down to here. That's because your main bearing is walking, and usually it's because the crank is forcing it to move front. Got it. So there's a lot of things going on. If you're using an aluminum block, and there isn't a specific aluminum bearing made for that, which in some applications are not. Keep in mind, there's thermal growth. I always like to keep the bore size closer to the minimum side. Get the plus or minus spec. Try to keep it to the minimum side, because that will make more stress on appropriate stress to hold the bearing in their what we call hoop stress. So
does the same kind of logic apply for the aluminum rod?
Absolutely.
Just go to the minimum side of the spec.
Minimum side of the spec, because that's going to give you the most crush on that bearing and not create to buckle.
So how would we find that spec? If somebody's watching this video and say, hey, I'm building an engine, where do I go to find that bore size spec, or housing bore size spec?
So those are the same specs, because most of the engine bearings are based off of OEM specifications. I mean, OEM specifications, the Clevite catalog has those specifications of what they're supposed to be, so that the plus or minus, and those are basically the same specifications as what the OEM came with. So, you know, OEM is the basis of what we do a lot of our racing off of. You know, we kind of make it the same spec, but now we will, again, if you're getting into, one thing I failed to mention, another difference between the H and the P bearing is the H bearing has more standoff than the P bearing. So
there's already more crush built
in an H. H and B would be the same. But the P bearing will have less crush in it than the H bearing, because it's not truly a performance thing. Eccentricity is different, bore relief is different. There's some other features that are different between them, but again, and the P is normally a centered, the H is always a cast.
Awesome. So to kind of wrap up, you got any do's and don'ts for the guys watching and gals watching, because we have both men and women, trade schools galore all around the country, educated engine builders and beginning engine builders, the whole crew. So what are some do's and don'ts based on your experience in putting them in engines and now knowing how they're made? Do's and don'ts.
So again, one big thing is stick with the spec. All right, when you know what you're building, know if it's a aluminum block, you need to be on the small side. Think about what you want to build before you're building the engine. If you're building...
That sounds familiar, by the way. Anyway, go ahead.
I didn't steal that from you.
No. I think it's a recurring theme throughout the Engine Performance Expo. It's like, you kind of need to plan out what your objective is before you start buying parts.
Absolutely. Hodgepodge of parts, sometimes it's a roll of the dice. Sometimes you're lucky, sometimes you're not. But think about, you know, what oil you're going to run. What RPMs are you going to run? You know, we didn't get into coated bearings. There's coated bearing options also. Coated bearings are really good. If you lose the oil film, it gives you a margin.
Yes. Oh, yeah.
It gives you a margin because it's a Mahle-based film. The other thing is I've found over and over and over, the bearing, if you get some issues going on with the bearing where you have some contact, the bearing, if you start seeing streaks in your bearing,
yes,
that is if you have, remember the overlay is copper tin lead or lead indium, that is usually what that is it's a frictional temperature that the softest, the lowest melting point component is starting to melt. Okay, so that's what you're seeing starting to streak through there. Okay. Right? And it's usually a streak mark, not contamination of grooves, but just dark marks. That is one of the overlays of frictional temperature, not necessarily oil temperature, frictional temperature of the bearing, creating oil temperature.
Got it.
So a coated bearing puts a layer, a thermal barrier between that overlay, because you still need the overlay to conform. The coating will put a thermal barrier to help protect the lowest heating value of your overlay from melting.
That's awesome. So I also, my own experience doing some bearing testing, using your bearings and using coatings on them, it's incredible in a thin film situation where we ran the engine at the edge of detonation with very low viscosity, at very low engine speed, and very high load, everything bad on purpose. Incredible the difference in what that, not only what the bearing looked like afterwards, right? So the coated bearing was way more durable in that case, but also when you start to have that bearing wear, that stuff goes everywhere else in the engine. So overall engine wear was actually higher when there was more bearing wear, because as it's feeding off particles, unfortunately the filters can't capture 100% of everything. So other thing too is now that, because that coating is a dry film lubricant, that when you start the engine up before that oil film is formed initially, you're adding protection. So for engines that see repeated start-stop cycles, coated bearings are the way to go, for certain.
When I first got involved in coated bearings in NASCAR, it was such a change, because you have to keep in mind a coated bearing is a very dark, and if you run a standard H bearing that's coated, it has this different color and kind of a gray. So you have to keep in mind, if you see fracturing, you see fatiguing, it's a color contrast that makes it look worse than what it really was, because now you have something that's black and you have something that's light. So it makes it an illusion that, oh my gosh, this has so much more. It's really not. What you're seeing is the light color cracks through a dark surface versus the same color light cracks going through the same color surface. So it makes it an illusion. So again, laying your parts out, reading it, and stop and think, okay, these are coated, and the color contrast between black and gray makes it pop as a more significant fatigue.
There's a huge tip right there alone on reading bearings. Understand the contrast of what you're looking at gives you calibration for doing the reading.
Exactly.
Awesome.
So listen to your parts; they don't lie.
No, preach on, brother, preach on.
Yes.
So that's some do's. What are some don'ts?
So the don'ts. A lot of people are really heavily involved, and they want to polish this bearing.
Thank you. I knew you were going to do that. Sorry. Go, keep on.
So I was guilty of that. Because you want to look good.
Let's raise your hand if you're watching. You ever take a newspaper and polish a bearing? Guilty as charged.
So the reality is, there's no purpose. All right. So once you put it, you want it clean, get any kind of oil off there, and beyond that, the bearing is perfectly fine as is. All right, because again, we're making eccentricities, and you're playing with tens of thousands of oil to create an oil wedge. So why would you want to go and take some light sandpaper or anything else and start changing what was designed to create proper oil flow, to put a proper oil wedge to give you most reliability out of your engine?
Risk reward sounds bad here.
It look pretty when you're sitting on the bench. And you're going to hold it together, somebody comes through and it's like, wow, those bearings look good. when you put the caps on there, you can't see it anymore.
Right, exactly.
I know that's kind of a lame way of saying it, but
it's true.
It is true. So it's the
polish
function.
the valve covers, not your bearings.
Exactly. The function of the bearing is a design part with very close tolerances. Plating is, we control plating to the 10,000s. I mean, how long a bearing is in seconds and temperature will control how thick that is. The machining is plus or minus to the tenths. You know, going to the solvent tank and clean it. Again, I was guilty. You know, and next person, you know, I want to clean the parting edges up because I want them to fit. That's not necessary.
Got it. Okay. Well, awesome, man. This was mind-blowing, wonderful information. So if they want to learn more about bearings, what's the best way for them to reach out?
So you can reach me at dan.begle, DANBEGLE, at Mahle.com. Feel free to shoot me an email. You have pictures of bearings you want to look at, talk about.
The catalog's got some failure analysis stuff in there, right?
Failure analysis. The catalog is a good reference of different things. Some more about what bearings are and some different things on there. So catalogs are always a great tool to have online, or we do have hard catalogs. This day and age, everybody's going online. So
oh yeah, it's really. Yeah.
Download the PDF.
Oh, exactly. Yeah, I've got it on my computer at home. Yeah, exactly.
Absolutely. So, but feel free, you know, reach out to me, dan.begle, B-E-G-L-E, at Mahle.com, and see if I can help you out with any bearing needs.
Well, Dan, thank you again so much for your time. We really appreciate it. Hope you guys and gals enjoyed this section.
We're back live here at the Engine Performance Expo. Dan Begle, Chuck Lynch. Learned a lot in that video. Dan queued up already for you, and that tells me there was a lot of interesting information coming through to the folks out there. If you do have a question, put it up in the chat section. We're going to hit Dan with it right now. But before we get to a couple questions, I just want to shout out to your day job in that this weekend, NHRA Thunder Valley Nationals, you'll be running around kind of checking out some of the bearing performance out there. Tell us a little bit about what you do at the track.
Yeah, so I go to Racetrack, and all the nitro fuel cars run Clevite bearings. Clevite bearings, we have a specific bearing made for them because of the amount of cylinder pressure that bearing goes through. The interesting thing is that the bearing will smash out because of how much cylinder pressure, and the engineers, the track crew chief, will figure out how to tune that engine based off how much that bearing is smashed. Original manufactured spec that we put it to, so it's pretty interesting to see that bearing smashed out that much and still have a successful run that it held together at the end of the racetrack.
Amazing. And coming out of your background, originally NASCAR,
correct.
Talk a little bit about the difference just in what you see at the conclusion of a run.
It's so much different because in NASCAR everything comes out and it needs to be the same shape, and small wear patterns, and the amount of cylinder pressure is a whole lot different, but the amount of time that bearing is, cycle count that it goes through, is so much more. So you look at those bearings, and then you come to the nitro fuel world where we're going this weekend in Bristol, and there's this day and night difference of the bearing looking out almost like it came out of the box versus, wow, I'm glad that made it to the end, but it's a precision make of tuning that engine to get the most out of that part, knowing that it's going to hang together.
That is amazing. And there's crazy stats out there that people can look up, but like a nitro engine only turns 570 times or something on a run. Just amazing stats that you don't realize and you don't think of. So if you got a question, put it in the chat section and we will get to it. Like Rick has got one. How do you set bearing clearances if not by housing rod bore sizes? Can't use factory min-max specs. Hopefully you can figure out what he's talking about there.
So with that, in a lot of performance bearings applications, and even in some standard OEM applications, we have a plus or minus 1. When the bearing is made, as we were talking about the eccentricity on the video, the parting lines are the same, so you can mix and match a -1 bearing to a standard bearing, and that would put a half thou to change your vertical clearance on that. So they make a plus and a minus off of the standard, and it's a thou, so you can go a thou to standard to a thou, or you can mix match and put it in a half thousandth of oil clearance and within that same housing, and not change the housing bore to achieve the right oil clearance.
And I would interject, do not change the housing bore, because you don't know what that crush height is, especially if you're using multiple bearing suppliers. So different steel back, they may not be having the same crush height and crush height load. So if you change the housing bore, you could have a failure.
Exactly.
So use the bearing wall thickness as your change.
Exactly. Yes.
And what would you say is the heart of the engine, as someone who is in the bearing biz?
The heart of the engine?
Yeah, this conversation we had just the other day, Chuck was in on.
Whoa. That's a tough one. Well, of course, a bearing guy, I'm going to say it's the bearings, right? Because, but no, in all seriousness, the bearing flow, the amount of oil that comes from a bearing, that's one of the major bearing leaking points, because you need oil to flow through the bearing to cool it, because the bearing will only, if you don't have enough oil flowing through it, then at that point the overlays will start to melt, and you need to cool it, just like a radiator. You need the radiator to cool the engine. You need cooling to go pass through the bearing, but you don't want too much, because at that point you can't get enough oil to pump through the engine, and you can deprive the oil in other components of the engine.
And that's that volume versus pressure argument that happens all the time.
Yes, exactly.
And I know that just from being a guy with a Pontiac engine. We got those giant main journals, and some of the guys modify the bearings because there's too much pressure, not enough volume, vice versa, etc. Talk a little bit about that.
Yeah, so you need a certain amount of volume to go through it. Pressure will create a hydrodynamic wedge, and volume is what you need to cool the bearing. So there is a balance between the two, that you don't want a whole lot of pressure in a tight oil clearance, because you can create a great oil wedge. But the problem is, if you don't get enough leakage through it, you can get a bearing that actually runs warmer, and the bearing is only as good as the lowest property of melting point of the overlay. And if you get frictional temperature, you can start melting the bearing out.
Which does not sound like a good thing.
That does not end well.
That is it. That's where parts failures happen. Well, Dan, it is great, and you'll be at the race this weekend.
Absolutely.
Doing your gig?
Yes.
Well, it's cool. We'll try to hook up. And a lot of people are reaching out. They're going to be heading out to the racetrack as well. All kinds of different high-performance racing engines out there. But I doubt we'll have any diesels in the house. But that can be rectified from time to time. What we're going to do right now, throw it to our next video, Cast Choate, talking about today's diesel of the day. What a day, what a day, what a day. Yeah, my brain is swollen. I've learned so much today. They told us, don't start cars. We are not going to listen.